Imagine looking up at the night sky and realizing that something from another star system is silently racing past us at incredible speed. In the summer of 2025, astronomers detected exactly that. A mysterious visitor from the depths of interstellar space that has been traveling for millions of years before finally reaching our solar system. This cosmic wanderer, known as 3I Atlas, represents only the third confirmed interstellar object ever discovered. Today we'll explore everything scientists have learned about this extraordinary celestial traveler and what it reveals about our galaxy. Discovery of 3I Atlas. Here's the moment that changed our understanding of interstellar visitors forever. On July 1, 2025, the Atlas telescope system at Rio Hurtado Observatory in Chile captured images of an unusual moving object racing through space at 61 kilometers per second. The Discovery team, led by Larry Deneau from the University of Hawaii's Institute for Astronomy, immediately recognized that this wasn't an ordinary asteroid or comet from our solar system. The object's hyperbolic trajectory and extreme velocity indicated it was following an escape path from our sun's gravitational influence. Initially catalogued as A11PL3Z, the mysterious visitor was positioned 4.5 astronomical units from the sun, approaching from the direction of Sagittarius. What made this detection particularly remarkable was that pre-discovery images dating back to June 14, 2025, revealed the object had been approaching undetected for weeks. The reason for this delayed discovery was its trajectory through the dense star fields near our galaxy's center, where countless background stars made it nearly impossible to spot against the crowded stellar backdrop. Within hours of confirmation, observatories worldwide began tracking this rare interstellar wanderer, setting the stage for one of astronomy's most significant discoveries. Atlas Survey System. But here's where this discovery became truly historic and earned its place in astronomical records. After extensive trajectory analysis by the Minor Planet Center, the object received its official designation as 3Y Atlas, where 3I signifies it as the third confirmed interstellar object in human history. This places it alongside the famous 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019. However, 3I Atlas quickly distinguished itself from its predecessors in a remarkable way. Karen Meach from the University of Hawaii and her international team confirmed on July 2, 2025, that the object was displaying clear cometary activity. Unlike Oumuamua, which remained enigmatically inactive throughout its visit, 3Y Atlas developed a visible coma and tail almost immediately after discovery. Observations from the Nordic Optical Telescope revealed the comet was clearly active with a distinctive tail measuring at least 25,000 kilometers in length. John Tonry, principal investigator of the Atlas project, noted that this discovery validated their sky survey system's capability to detect rare astronomical phenomena. The rapid identification of cometary activity made 3Y Atlas the second confirmed interstellar comet, providing scientists with an unprecedented opportunity to study active sublimation processes in a visitor from another star system. Object classification and naming. Now prepare to be amazed by the sheer scale of this interstellar giant. Recent observations conducted by Marco Micheli from the European Space Agency using the Vera C. Rubin Observatory have determined that 3Y Atlas measures approximately 11.2 kilometers in diameter, making it significantly larger than both previous interstellar visitors combined. This massive size has profound implications for scientific study, as larger objects retain more of their original composition and provide clearer observational targets for detailed analysis. The comet's substantial nucleus is surrounded by an active coma that exhibits a distinctly reddish coloration, remarkably similar to what was observed in 2I Borisov. Daryl Seligman from Michigan State University, who led the initial characterization studies, noted that this color similarity suggests interstellar comets may share common compositional characteristics regardless of their stellar origin. The impressive scale of 3Y Atlas means it will remain visible to Earth-based telescopes for an extended period, giving researchers months rather than weeks to conduct comprehensive observations. This extended visibility window represents a golden opportunity for the astronomical community to gather unprecedented data about interstellar comet composition, structure, and behavior as it interacts with our sun's radiation and solar wind during its passage through our solar system. Orbital characteristics. Okay, here's something that will really blow your mind about this cosmic time capsule's incredible journey through space. Based on detailed orbital mechanics calculations performed by Davide Farnochia at NASA's Jet Propulsion Laboratory, scientists believe that 3I/Atlas actually originated from the Milky Way's thick disk region, where ancient stellar populations reside. This means the comet is potentially around 7 billion years old, which is, well, older than our entire solar system by approximately 2.5 billion years. Its epic journey likely began when gravitational perturbations from massive planets or maybe even close stellar encounters ejected it from its birth star system eons ago. For millions of years, this ancient wanderer drifted through the frigid vacuum of interstellar space at temperatures approaching absolute zero, which honestly perfectly preserved its primordial composition like a cosmic freezer. Sam Dean, an amateur astronomer who helped identify additional pre-discovery observations, contributed to tracking the comet's path backwards through time. The comet's trajectory suggests it has been traveling through the galaxy's spiral arms, potentially witnessing the formation and destruction of countless star systems during its incredible voyage. This preservation makes 3I/Atlas an invaluable scientific specimen, carrying within its frozen nucleus the chemical signatures and formation conditions that existed in a distant star system billions of years ago, offering unprecedented insights into galactic evolution and early planetary system formation processes. Physical properties. But here's what makes this discovery even more extraordinary: the unprecedented international scientific collaboration that made it possible. The research effort was spearheaded by Michigan State University's Darrell Seligman, who coordinated with a global network of observatories and research institutions to maximize observation time and data quality. Robert Warwick from the University of Western Ontario, who previously discovered 1I Oumuamua, provided crucial expertise in interstellar object identification and tracking protocols. The collaborative team included researchers from the European Southern Observatory, NASA's Goddard Space Flight Center, and the Harvard-Smithsonian Center for Astrophysics, really demonstrating how modern astronomy relies on rapid international cooperation. Grigory Fedorets from Queen's University Belfast contributed orbital dynamics expertise, while Tony Farnham from the University of Maryland provided cometary activity analysis. This coordinated effort represents one of the most comprehensive rapid response campaigns in astronomical history, with over 50 professional observatories and numerous amateur astronomers contributing observations within the first month of discovery. The team's ability to quickly organize this global response ensured that critical early observations were captured before the comet's activity levels changed, maximizing the scientific return from this rare interstellar visitor and establishing new protocols for future interstellar object studies. Comet activity features. Now let's trace the incredible path this ancient wanderer will take through our solar system over the coming months. 3I/Atlas will reach its closest approach to the Sun, called perihelion, on October 29, 2025, at precisely 11:41 Universal Time. At this crucial moment, it will be positioned 1.36 astronomical units from the Sun, that's about 203 million kilometers away, perfectly situated between the orbits of Earth and Mars. This optimal distance means the comet will experience significant heating without being destroyed by extreme solar radiation. During its approach phase, the comet will have several notable planetary encounters that provide unique observational opportunities. On October 3, 2025, it will pass just 0.19 astronomical units from Mars, only 28 million kilometers away, potentially allowing Mars-based instruments to conduct close-range observations. Following perihelion, the comet will swing past Venus on November 3, 2025 at a distance of 0.65 astronomical units. Most importantly for Earth-based observers, our planet remains completely safe throughout this cosmic dance. The closest 3I/Atlas will approach Earth is 1.8 astronomical units on December 19, 2025. That's about 270 million kilometers away, providing excellent viewing conditions while maintaining a comfortable safety margin. This trajectory offers astronomers multiple observation windows from different vantage points throughout the solar system. Amateur contributions. Here's where the scientific excitement reaches its peak: the detailed analysis of this interstellar visitor's composition and structure. Spectroscopic observations conducted by Alan Fitzsimmons from Queen's University Belfast using the Gemini Observatory have revealed that 3Y Atlas is composed primarily of water ice, silicate minerals and organic compounds similar to comets in our own solar system. However, the presence of exotic isotopic ratios in its gas emissions suggests formation conditions significantly different from our local environment. Bin Yang from the European Southern Observatory detected unusual concentrations of deuterium-rich water vapor, indicating the comet formed in an extremely cold environment around a different type of star. As the comet approaches the Sun, increasing solar radiation is causing accelerated sublimation of volatile ices, revealing deeper layers that have remained frozen for billions of years. Jacqueline Keane from Boston University has identified traces of carbon monoxide and methane in the comet's tail, providing insights into the chemical conditions of its birth star system. The James Webb Space Telescope, under observations led by Stephanie Malam from NASA Goddard, has been scheduled to conduct detailed infrared spectroscopy to identify complex organic molecules that might exist within the comet's nucleus. These compositional studies are providing unprecedented insights into star formation processes and the distribution of life-building molecules throughout our galaxy. Surface composition. But here's what makes this observation campaign truly revolutionary: the unprecedented coordination of space-based and ground-based telescopes working together. Paul Chodas from NASA's Center for Near-Earth Object Studies has coordinated orbital predictions that allow telescopes to track the comet with extreme precision. The Hubble Space Telescope, under the direction of Matthew Knight from the Naval Research Laboratory, captured high-resolution images on July 21, 2025 that revealed intricate details of the comet's coma structure and dust distribution patterns. Ground-based facilities including the Very Large Telescope in Chile and the Keck Observatory in Hawaii have been providing continuous monitoring of the comet's brightness changes and spectral evolution. Quanzi Ye, from the University of Maryland, has been leading photometric studies that track how the comet's activity levels change as it approaches the Sun. The NEOWISE Space Telescope has been measuring infrared emissions to determine the comet's temperature distribution and internal heat sources. This coordinated campaign represents the most comprehensive study of an interstellar object ever conducted, with data collection continuing through September 2025, before the comet passes too close to the Sun for safe observation. The wealth of data being collected will provide material for scientific studies for decades to come, advancing our understanding of interstellar chemistry and planetary system formation processes. Interstellar object density. Now here's something that sounds like science fiction but is being seriously considered by space agencies worldwide. Atsuhiro Yaginuma, an undergraduate researcher working with Daryl Seligman at Michigan State University, is conducting detailed trajectory analysis to determine whether a rapid spacecraft mission to 3Y Atlas might be feasible. The challenge is enormous. Intercepting an object moving at 61 kilometers per second would require unprecedented propulsion technology and launch timing precision. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has been evaluating existing spacecraft designs that could potentially reach the comet during its closest approach to Earth in December 2025. Such a mission would need to launch within months of the discovery, requiring massive international cooperation and emergency mobilization of space resources. Alan Stern, principal investigator of the New Horizons mission, noted that while technically challenging, the scientific payoff from getting close to an interstellar object would be revolutionary. A successful intercept could provide direct samples of materials from another star system, potentially containing organic compounds or even microscopic signs of extraterrestrial life. Even if a full intercept proves impossible, the research being conducted is advancing rapid response space mission capabilities and establishing protocols for future interstellar object encounters. The mere possibility represents a remarkable leap in humanity's ability to explore beyond our solar system. Origins and age speculation. Finally, here's the most profound implication of this discovery for the future of astronomy and our understanding of the cosmos. The detection of 3I Atlas, following Oumuamua and Borisov, is providing statistical evidence that interstellar objects are far more common than previously estimated. Mark Norris, from the University of Central Lancashire, has calculated that approximately one interstellar object larger than 100 meters passes through our solar system every year, though most remain undetected. Robert Jedicke from the University of Hawaii estimates that the Atlas survey system, with telescopes in Hawaii, Chile, and South Africa, will detect several interstellar objects annually as technology improves. The Vera Rubin Observatory, scheduled to begin full operations in 2025, is expected to revolutionize interstellar object discovery with its ability to scan the entire visible sky every few nights. Michelle Bannister from the University of Canterbury predicts that within a decade, we'll have discovered dozens of these cosmic wanderers, providing a statistical sample large enough to understand galactic dynamics and planetary system evolution. Each new discovery adds pieces to the puzzle of how materials and potentially life itself might be distributed throughout our galaxy. 3. I-Atlas isn't just a single remarkable discovery, it's opening an entirely new field of astronomy that studies the messengers traveling between star systems, carrying secrets from across the galaxy. From its ancient origins in the thick disk of our galaxy to its spectacular journey past our sun, 3I-Atlas has revolutionized our understanding of interstellar visitors and the materials that travel between star systems. This cosmic time capsule, preserved for billions of years in the cold of space, continues to reveal secrets about distant worlds and the formation of our galaxy itself. As we track its departure back to interstellar space, we can only wonder what other mysteries await discovery. Like, share, and subscribe to InnoVision Tech for more cosmic revelations. A comet that shouldn't exist just forced the James Webb Space Telescope into emergency mode, and its data confirms a chemical nightmare breaking every rule in the book. The numbers are terrifying astronomers, pointing to something far stranger than a simple interstellar visitor. Is this object even natural, or is something else hurtling straight for us? The stakes only get higher from here. Let's explore this together. Emergency override. Webb's unprecedented response. What does it take to derail the most powerful space telescope ever built? On August 6, 2025, we found out. The James Webb Space Telescope slammed into emergency mode, pausing its entire science program for the first time in years. This wasn't a scheduled observation, it was a high-stakes director's discretionary time override. A procedure so rare it's only the fourth such event since launch in 2021. The target, an interstellar object designated 3I-Atlas, ground-based telescopes had just flagged it for accelerating in ways no one could explain, its spectrum flashing with unexpected metals. The call was authorized directly by the Space Telescope Science Institute director, Dr. Kenneth Sembach. The chain of command was short and swift, bypassing the usual committees that schedule Webb's time months in advance. The risk was immense. Webb's schedule is a precise ballet of fuel and orbits. A single, unplanned maneuver to observe a target for 5.3 hours could cost a week of other science. But the window to catch 3I-Atlas was closing fast. Its trajectory was shifting by the hour. The command was uploaded and the telescope pivoted, its near-infrared spectrograph, NIRSpec, locking onto a target that was rewriting astrophysics in real time. This wasn't a routine target of opportunity, it was a scramble to observe an object challenging our fundamental understanding of visitors from other star systems. Early activity beyond Jupiter's orbit. Here's where the story gets strange. Comets are supposed to be dormant deep freeze travelers. They wake up when they get close to the sun, typically inside Jupiter's orbit at 5 astronomical units. But 3I-Atlas started showing activity far out, at 6 AU from the sun. That's nearly 900 million kilometers away, where temperatures hover around a frigid 110 Kelvin. The first hints came from the Pan-STAR survey in Hawaii, led by Dr. Ken Chambers, which noted a faint, persistent brightening. It wasn't just a flash, the object was waking up. Then the 8.1-meter Gemini South telescope in Chile confirmed it. 3I-Atlas was already sprouting a tail, a ghostly limb of gas stretching hundreds of thousands of kilometers. This is not how comets are supposed to behave. For comparison, 2I Borisov, discovered by amateur astronomer Gennady Borisov, began its activity much closer. The early outgassing of 3I-Atlas suggested its engine wasn't the sublimation of water ice. Something far more volatile was driving this activity, a clear sign this visitor came from a place with a very different chemistry. It was the first clue that 3I-Atlas was a messenger carrying a very strange message, one that began long before it should have. The carbon dioxide anomaly. The moment Webb's NIRSpec instrument locked on, the chemical picture came into focus, and it was a shock. The spectrum was overwhelmed by carbon dioxide. In the cold depths of space, CO2 ice turns to gas at much lower temperatures than water ice, explaining the early activity. But the sheer quantity was staggering, with a production rate exceeding 10 to the 28th molecules per second. Webb's data revealed a carbon dioxide to water ratio of 8 to 1. Let me put that in perspective. A typical comet from our solar system like Hale-Bopp has a CO2 to water ratio of about 20%, or 0.2 to 1. The Interstellar Comet 2 I Borisov had a ratio of about 0.4 to 1. 3I Atlas was 20 times more CO2 rich than Borisov. As Dr. Neil Dello Russo of Johns Hopkins APL, an expert in cometary composition, would note, this is completely unprecedented. The data was undeniable, with the telltale signature of CO2 at a wavelength of 4.26 microns burning bright and broad. Water was there, but only as a faint afterthought. This wasn't just a comet with extra CO2, it was a body fundamentally built differently, pointing to a birthplace where water might be a trace element, a type of protoplanetary disk our models barely account for. Nickel without iron, an impossible chemistry. But the carbon dioxide was just the appetizer. The main course was a chemical puzzle that sent shockwaves through the astronomical community. Webb's spectrum showed clear, strong signatures of metallic nickel. At first, the team suspected an instrument artifact, but the lines held firm, confirmed by the Very Large Telescope's UVS spectrograph operating at a resolving power of 80,000. The nickel was real, with a production rate of 10 to the 21st atoms per second at 3.8 astronomical units. But here's the impossible part: there was no iron. In every celestial body ever studied, the cosmic abundance ratio is about 15 parts iron to 1 part nickel. 2I Borisov followed this rule. 3I Atlas shattered it. The data showed that nickel outnumbered iron by more than 40 to 1. Imagine finding a pure platinum nugget with no trace of other platinum group metals. That's the scale of this anomaly. Spectroscopists like Dr. Dennis Bodowitz, an expert on cometary composition, would be stunned. The nickel lines at 3,415, 3,524, and 3,525 angstroms were unmistakable. But the spectrum was flat, where iron should have been. One fringe theory suggests the formation of nickel carbonyl, a highly volatile molecule, but for this to happen without its iron equivalent defies all known astrochemistry. Trajectory anomalies and acceleration spikes. As the chemical data was being analyzed, the teams tracking the comet's path were facing their own bewildering problems. 3I Atlas was not following the clean, predictable arc of gravity. It was accelerating, showing a non-gravitational change in velocity of nearly 0.12 meters per second squared over just 72 hours. While comets do this, the force is usually gentle. The acceleration of 3I Atlas, however, wasn't smooth. The trajectory, tracked by the Minor Planet Center, showed tiny, sharp jumps. This recalled the mystery of Oumuamua, whose own non-gravitational acceleration was famously detailed in a 2018 paper by Marco Micheli. But this was different. For an object estimated to be 11 kilometers across, this is like watching a mountain suddenly shift course. The Pan-STARRS survey team ran every diagnostic, checking for software bugs or errors in their astrometry. The data was solid. The acceleration was real. It meant the forces acting on 3I Atlas were not just coming from the sun. Something else was at play, something internal, or something about its structure that allowed it to move in a way that defied our models, deepening the mystery and fueling speculation that this was no ordinary cosmic iceberg. The lighthouse effect. Mechanical light curves. The weirdness didn't stop with its chemistry or its path. The way 3I Atlas reflected sunlight was just as puzzling. Photometric data from Gemini South and the TESS Space Telescope revealed a periodic brightening, a sharp pulse of light that repeated every 7.2 hours with almost mechanical regularity. It was like a lighthouse beam. A slow, gentle tumble is expected from an outgassing comet. But this was different. The brightness changed by over 2 magnitudes, a factor of 6, which is an extreme variation. The period was too constant. Dr. Karen Meach of the University of Hawaii, who led the team that characterized Oumuamua's wild tumble, would find this regularity highly unusual. For a normal comet, the spin should slow as it loses mass, but the 7.2-hour period remained locked in. Astronomers tried to model it as a spinning, elongated object, but the sharp rise and fall of the light curve didn't fit well. Other models suggested a hollow or even a sheet-like structure with sunlight glinting off a large, flat, reflective surface. The parallels to Oumuamua were impossible to ignore, but 3Y Atlas was bigger, brighter, and its light curve was even more pronounced, more rhythmic, pushing the boundaries of what a natural object could be. Ancient sky metal. Historical context. The idea of metal falling from the sky isn't new, it's woven into our history. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't possibly have smelted. Analysis of artifacts from the Gertza tombs reveals the secret. The beads contain nearly 30% nickel. No terrestrial ore has that composition. The only source was a rare type of meteorite called an ataxite. A similar story is found in Tutankhamun's tomb. Buried with him was a dagger with a blade of meteoritic iron containing 11% nickel and 0.6% cobalt, a composition detailed in a 2016 study in Meteoritics and Planetary Science. This iron from heaven was incredibly rare. The Babylonians also watched the skies, and their cuneiform tablets speak of burning stones as omens. The Akkadian word for iron, and bar comma, is sometimes translated as sky metal. These cultures didn't understand the chemistry, but they knew this metal was different, special, and came from beyond their world. They understood that when the sky delivers something new, it can be both a wonder and a warning. Today, astronomers use powerful telescopes, but the core question remains. When an object arrives with a signature that defies explanation, what message is it bringing? Avi Loeb's challenge to consensus. As the data on 3I Atlas circulated, one voice cut through the cautious scientific debate. Harvard astrophysicist Avi Loeb. He had already made waves with his controversial hypothesis that Oumuamua could be an extraterrestrial artifact. Now, faced with 3I Atlas, he was even more direct. In a widely read blog post, he posed a blunt question: what natural process can produce a comet with pure nickel and no iron? He pointed out that separating these elements requires complex industrial processes. In the cosmos, it's considered impossible. Loeb connected the dots: the impossible chemistry, the erratic acceleration, the clockwork light curve. He argued that we must consider the possibility that we are looking at technology, a central mission of his Galileo project. His critics urged caution, but Loeb's position is that the anomalies themselves are the evidence. He contends that clinging to a natural origin explanation when the data contradicts it is unscientific. His challenge forced the conversation into the open, pushing the debate beyond academic journals and into the public square, demanding that the artificial hypothesis be considered on its own merits. Scientific community divided. The case of 3I Atlas split the astronomical community. On one side were scientists working to find a natural, if exotic, explanation. Dr. Alan Stern, principal investigator of the New Horizons mission, had previously proposed that Oumuamua could be a nitrogen iceberg from a Pluto-like exoplanet. Perhaps 3I Atlas was a carbon dioxide iceberg from a similar world. Others, like Comet expert Dr. Matthew Knight, argued that the non-gravitational acceleration could still be explained by powerful localized jets. On the other side were those emboldened by Loeb, who argued that we had to take the artificial origin hypothesis seriously. They pointed out that a light sail, a thin reflective sheet, could neatly explain both the sharp light curve and the acceleration. No one was claiming definitive proof, but the idea that 3I Atlas might be a probe, or a fragment of one, was no longer a fringe theory. It was being actively discussed. Peer-reviewed journals and online forums buzzed with debate as every new piece of data was scrutinized. The object was a cosmic Rorschach test, and what you saw depended on how willing you were to challenge fundamental assumptions about our place in the universe. NASA's high anomaly classification. Behind the scenes, the official response was one of cautious urgency. While public statements remained measured, NASA's Planetary Defense Coordination Office, led by Officer Lindley Johnson, quietly flagged 3I Atlas with a special designation high anomaly. This classification is typically reserved for near-Earth objects whose behavior is unpredictable. But in this case, it was for an object whose very nature was in question. It wasn't a threat in terms of impact, but it was a scientific wildcard of the highest order. Internal risk assessments using systems like Sentry-2, usually focused on collision probabilities, were repurposed to track an enigma. The official line from NASA remained consistent: more data is needed. Extraordinary claims demand extraordinary evidence. Yet in private, even the most skeptical scientists admitted this object was unique. The data was being triple-checked and distributed to a wider network of researchers. But until a consensus emerges, 3I Atlas remains an official mystery, an object whose strange behavior has earned it a unique place in NASA's catalog of cosmic visitors. So what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system whose chemistry is alien to us, or is it something more? The evidence is tantalizing and deeply unsettling. An object that moves on its own, shines with a mechanical rhythm, and is made of materials that shouldn't exist in nature. It could be the first definitive proof that we are not alone in the universe, a piece of technology from a civilization far beyond our own. For now, the answer hangs in the balance, locked in the data awaiting the next observation that could finally tip the scales. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching InnoVision Tech. What if a comet entered our solar system and broke every rule we thought we knew? Imagine an object that defies the fundamental laws of physics, sporting a feature that looks less like nature and more like engineering. This isn't science fiction. It's a thought experiment grounded in a torrent of strange data from real interstellar visitors. We're about to explore a hypothetical scenario based on real science that pushes the boundaries of understanding. Let's delve into it together. The Chilean frame. It all starts with a single unexpected image. Imagine an amateur astronomer, much like the legendary Gennady Borisov who discovered the first confirmed interstellar comet from his backyard Margot Observatory, peering at the sky from the clear darkness of Chile's Atacama Desert. The date is October 20th, 2025. Her equipment, a 150mm refractor, is pointed at the coordinates for a newly tracked interstellar object, 3I Atlas. What comes back from her cooled CMOS camera after a 60-second exposure isn't a textbook comet. The raw data, captured under pristine, verifiable conditions with atmospheric seeing logged at an exceptional 0.7 arcseconds, shows something impossible. This isn't a blurry social media rumor, it's a hard data point from a credible observer. The coordinates match NASA's official Jet Propulsion Laboratory tracking. The equipment metadata is clean, and the image is perfectly sharp. And there, aimed directly at the sun, is a perfectly straight, highly collimated jet of material. This single frame from a small, converted farm building becomes the most important astronomical image of the decade, kicking off a firestorm of debate and challenging the very foundation of cometary science.
Comet Physics 101.
So, why is a sunward-pointing jet such a big deal? First, let's cover the basics. Comets are often called cosmic snowballs, a term coined by the brilliant astronomer Fred Whipple back in 1950. His model describes a nucleus made of ice, dust, and rock. As a comet approaches the sun, solar radiation heats its surface, causing ices like water to turn directly into gas, a process called sublimation, at temperatures above -100 degrees Fahrenheit. This process creates a glowing atmosphere around the nucleus called a coma. The sun's influence doesn't stop there. It produces two distinct forces: radiation pressure from photons and the solar wind, a stream of charged particles traveling at over 400 kilometers per second. As explained by solar physicist Eugene Parker, these forces push the gas and dust away, forming two tails. The dust tail is broad and curved. The ion tail, made of charged gas, is thinner and points directly away from the sun, like a windsock in a gale. No matter where the comet is in its orbit, the rule is unwavering. The tails always point away from the sun. This is fundamental observable physics, seen in every comet we've ever studied.
The sunward jet.
Now let's go back to that Chilean frame. It throws the rulebook out the window. Instead of a fuzzy coma and majestic tails pointing away from the solar glare, the image of 3I Atlas shows something entirely different. The nucleus is a sharp, dark point. The surrounding coma is strangely faint, with a measured magnitude of only 18.5, far dimmer than expected. But the most shocking feature is a narrow, focused column of material, no more than 2 arcseconds wide, extending from the nucleus directly toward the sun. It's not a tail, it's a jet. Seasoned comet observers, like the renowned planetary scientist David Jewett, would find this image deeply unsettling. The expected anti-solar tail is completely missing, replaced by a feature that seems to violate the basic principles of solar-driven outgassing. The object is actively resisting a 400 km/s solar wind. The image confronts us with a stark contradiction. An object that should be fleeing the sun's power appears to be pointing something straight at it. This single observation demands an explanation, and the easy answers simply don't hold up.
Breaking the rules.
Let's be clear about how profoundly this hypothetical image breaks the standard cometary model. The physics of solar sublimation dictates that as a comet gets closer to the sun, it should become more active, the coma should brighten, and the tail should grow longer. Under the excellent viewing conditions logged in Chile, a normal comet at this distance would be expected to brighten by at least a full magnitude, displaying a luminous coma and a clearly visible tail. Yet, 3I Atlas shows a minimal coma, and its only significant feature is a jet running in the completely wrong direction. Scientists like Imre Toth, who specialize in comet activity, would immediately suspect an equipment malfunction. Could it be an artifact, like a sensor streak? The data suggests no. The feature is too sharp, too perfectly aligned with the sun's position, and it persists across multiple, independent processing attempts of the raw data. It's too regular to be random noise. We are left with a data point that suggests the rules of sublimation and solar pressure are, for some reason, not applying to this object, a conclusion no scientist would reach lightly.
The gauntlet.
Every extraordinary claim in astronomy must survive a gauntlet of mundane explanations. The first suspect is always geometry. Sometimes, from Earth's specific vantage point, dust left in a comet's orbit can create an anti-tail. However, anti-tails, studied extensively by scientists like Michael S. P. Kelly during NASA's EPOXY mission, only appear when Earth crosses the comet's orbital plane. On October 20th, Earth was still over 4 degrees away from the orbital plane of 3I Atlas, making a prominent anti-tail highly improbable. More importantly, anti-tails are always broad, diffuse sheets of dust, not the tightly focused jet seen in the image. The next suspect is a transient event, like a pocket of volatile ice erupting. But these outbursts are chaotic and short-lived, rarely lasting more than a few rotations of the nucleus. The sun-facing feature in the Atlas data is persistent across more than 4 hours of observation, making a fleeting eruption unlikely. Finally, atmospheric distortion is ruled out by the observatory's logs. The stars in the image are sharp, proving the sky was stable. After running the checklist, every conventional explanation falls short of explaining the hard data.
Chemical anomalies.
The weirdness isn't just visual. Spectroscopic analysis of 3I Atlas reveals a chemical composition that is bizarre, even for an interstellar traveler. The data shows a carbon dioxide to water ratio of nearly 8:1, one of the highest ever recorded. For comparison, the famously CO2-rich Comet C 2016 R2 Pan-STARRS had a ratio of about 5:1. This tells us 3I Atlas was formed in a place far different from our own solar system's water-rich environment. But the real smoking gun is the metal content. Preliminary spectra from observatories like the Keck telescope hint at the presence of nickel emission lines, but with a strange absence of iron. In all typical cometary material, iron is at least 10 times more abundant than nickel. The data from 3I Atlas suggests a nickel-rich, iron-poor outflow, a pattern with no known natural precedent. Scientists like Denis Bodowitz, who studied the chemistry of 2Ri Borisov, would be stunned by these readings. The unique chemistry suggests a nucleus with properties we've never encountered, deepening the mystery of the sunward jet.
Retrograde path.
The object's path through our solar system is another major red flag. 3I Atlas is on a retrograde orbit, with an inclination of 110 degrees, meaning it's traveling against the flow of planetary traffic. Its immense speed, with a hyperbolic excess velocity measured at 32 kilometers per second, absolutely confirms its interstellar origin. It's a tourist here, not a resident, but its trajectory, combined with its estimated mass, raises fascinating questions. When scientists like Avi Loeb analyzed the first interstellar object, Oumuamua, its slight deviation in trajectory led to the hypothesis that it could be an artificial object, a solar sail. Now, with 3I Atlas, we have a different anomaly. It's not a subtle acceleration, it's a visible, persistent structure that seems to defy solar forces. This sun-facing jet, in the context of its exotic composition and retrograde path, forces us to consider possibilities that stretch natural explanations to their breaking point. Could this jet be a functional feature perhaps, as propulsion expert Mason Peck has theorized in other contexts, an engineered structure for orbital maneuvering?
Perihelion blindness.
Here's where the timing gets critical. The comet is scheduled to reach perihelion, its closest approach to the Sun, at a distance of 0.4 astronomical units, on October 29th. At that exact moment, it will be hidden from our view, positioned directly behind the Sun in a solar conjunction. This creates a week-long observational blackout for all ground-based telescopes on Earth. Any sudden change in behavior, a fragmentation, a course correction, or a massive energy release could happen completely undetected. During this period, our only eyes on the comet belong to a handful of space-based instruments. The SOHO Observatory's coronagraph can spot large-scale outbursts, while the Parker Solar Probe might record changes in brightness. But honestly, the data will be patchy and delayed. As Noor-e-Rawafi, the project scientist for Parker Solar Probe, knows well, these instruments are designed to study the Sun, not hunt for cometary anomalies. This period of perihelion blindness is the perfect time for something extraordinary to happen, unseen by human eyes.
Space Watchers.
Once 3I Atlas emerges from behind the Sun in early November, an army of telescopes will be waiting. The scientific community will be on high alert, and the checklist of what to look for is clear. First is photometry. A sudden jump in brightness could signal a natural outburst, while a steady fade without a growing tail would be highly unusual. Next is morphology. Does the comet finally grow a classic anti-solar tail? Or does the bizarre sunward jet persist? Programs like Pan-STARRS, directed by astronomers such as Ken Chambers, are designed for this kind of monitoring and can detect objects down to a magnitude of 24. They will search for any fragmentation, the appearance of smaller companion objects breaking off the main nucleus. Even tiny, almost imperceptible shifts in its trajectory, measured with a precision of milli-arcseconds, will be meticulously tracked by professional networks. Every new piece of data will be scrutinized, compared, and debated by experts like comet dynamicist David Nesvorny. The weeks following the solar conjunction will be a critical test for all existing theories.
Emergence.
As the first post-perihelion images arrive, the scientific process will kick into high gear. Interpreting the new data will demand extreme caution. Image processing techniques, how you stack frames or subtract background light, can easily create or hide faint features. A jet that is visible in one astronomer's processed image might vanish in another's. The key, as always, will be reproducibility and peer review. As emphasized by researchers like Michelle Bannister, a claim is only as good as the independent evidence that supports it. No single image will be enough. The global astronomy community will need to achieve a high signal-to-noise ratio, ideally greater than 5, across multiple independent datasets to confirm any anomalous feature. Only a structure that appears consistently can be considered real. The story of 3I Atlas will ultimately be written not by a single dramatic snapshot, but by the slow, careful, and rigorous work of scientists checking, rechecking, and challenging each other's findings. The truth will be found in the consensus of global data. So, we are left standing at a precipice. A hypothetical object, 3I Atlas, backed by puzzling data from real interstellar visitors, forces us to confront the limits of our knowledge. Is its sunward jet a fleeting natural phenomenon, a sign of exotic chemistry we've never seen before? Or is it something that fundamentally bends the rules of physics, hinting at a purpose beyond natural formation? The period of perihelion blindness leaves us in suspense, but the weeks that follow promise a flood of new data. The answers are waiting out there, in the cold dark of space. What do you think is happening with this object? Let us know in the comments below. And don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. Thanks for watching InnoVision Tech.